Hi everyone, in the first bottled experience video, we used parallel lines as a way of figuring out why the angles inside a triangle add up to 180 degrees. So what I'd like to do here is quickly run through why parallel lines worked for this purpose. So first, we need to look at what parallel lines are. Parallel lines are two straight lines that always stay the same distance apart. What this means is those two straight lines are moving in the same direction, have the same gradient if you're trying to plot out their equation, and they never intersect. Some of the properties that we used when we were trying to actually solve for our triangles was what happens when there's a line that crosses over both of the parallel lines. The important thing here is that line is a straight line. Well, the first thing we get is because of the fact that these lines are going in the same direction, there will be these two angles labeled in blue which are corresponding to each other. These angles are defined as being always equal to each other because of the fact that the parallel lines are going in the same direction. You can think of it as the fact that we're using this line that's crossing over them to actually check that they're going in the same direction. The next rule that we can use are these two angles marked with the green crosses. They are the alternate angles. They are inside the parallel lines and on opposite sides of the line that's crossing over them. They are also always equal. This is because of the way that the straight lines interact. This is the rule that we use to help us show that the triangles add up to 180 degrees, and it's a direct result of the way the corresponding angles interact. Finally, as a result of all this, we get the co-interior angles. These are the ones inside the parallel lines, but on the same side of the line that's crossing them. They add up to 180 degrees. This is again the result of the way the corresponding angles react to the intersection between two straight lines. As when a 180 degree angle is cut into two parts, both parts must add to 180 degrees. This leads us to an interesting effect. If we draw out a triangle, and we're going to draw it so that the base here is vertical, the two base angles and the angle at the tip must add up to 180 degrees. This is what we proved earlier. But if I grab the tip of this triangle and start pulling it out further and further, we see that the two angles at the base get larger and larger. The angle at the tip gets smaller and smaller and smaller. If I were to drag the tip of the triangle an infinite distance away, we would see that angles A and B here would have to become 90 degrees, and the angle C would end up being 0 degrees. So what we've actually formed here is both a set of parallel lines and a triangle which has two angles of 90 degrees. And because we know we took the point where the two lines meet and dragged it to infinity, we know that this is a real triangle. This sort of manipulation of numbers, where we take something to infinity, or in some cases bring something to 0 that can't get there, can still give us a powerful tool which we can use to solve problems that affect our everyday lives, and give us another way to find a triangle with two 90-degree angles.